Awesome. So today we're gonna take a look at the Secureum race. We're doing, I believe, the first race, which is Ethereum 101. So we're just gonna start reading these and going through everybody. Once again, you can open your mics, ask. Raji here is here, and enemies. And so let's go. So first thing is Ethereum is a next generation smart contract and decentralized application platform. Okay, Ethereum is a blockchain built into a computing programming language, allowing anyone to write smart contracts and decentralized application where they can create their own arbitrary rules for ownership, transaction formats, and state transition functions. Okay, it's really important to understand this part. You know, when we talk about state transition, this is a very specific thing in a blockchain context. You know, that's even maybe that's even why you have this seat here. So Ethereum is open source. Ethereum is an open source, globally decentralized computing infrastructure that executes programs called smart contracts. It uses blockchain to synchronize and store state changes, along with a cryptocurrency called Ether to meet and constrain execution's resource costs. It is often described as the word computer. Ethereum, the platform, enables developers to build powerful decentralized applications with built-in economic functions while providing high availability, auditability, transparency, neutrality, and it also reduces or eliminates censorship and reduces certain counterpart risks. Ethereum purpose is not primarily to be, sorry guys, Ethereum purpose is not primarily to be a digitalized currency payment network. While the digital currency Ether is both integral and necessary for the operation of Ethereum, Ether is intended as a utility currency to pay for the use of the Ethereum platform as the word computer. They're pretty much saying the same thing on the first five items, but that's okay. Unlike Bitcoin, which has a very limited scripting language, Ethereum is designed to be a general purpose programmable blockchain that runs a virtual machine capable of executing code of arbitrary and unbounded complexity. Where Bitcoin's scripted language is intentionally constrained to the simple true-false evaluation of spending conditions, Ethereum language is Turing complete, meaning that Ethereum can straightforwardly function as a general purpose computer. The original blockchain, named Bitcoin blockchain, tracks the state of units of Bitcoin and their ownership. You can think of Bitcoin as a described consensus state machine, where transactions caused the global state transition alter the ownership of coins. The state transactions are constrained by the rules of consensus, allowing all participants to eventually converge on a common state of system. After several blocks are mined, Ethereum is also a distributed compute, sorry guys, converge on a common state system after several blocks are mined. Ethereum is also a distributed state system machine, but instead of tracking only the state of the currency, Ethereum keeps track of state transitions of a general purpose data store and it stores everything in a key pair tuple, okay? Ethereum core component is a P2P network. Ethereum runs on the Ethereum main network, which is addressable by the TCP port 30303 and runs on a protocol called dev P2P. Transactions. Ethereum transactions are network messages that include, among other things, a sender, a recipient, a value, and a data payload. State machine. Ethereum state machines are processed by the Ethereum virtual machine, a stack-based virtual machine that executes bytecode machine language instructions. EVM programs, called smart contracts, are written in high-level languages like Solidity or Viper, and Viper is much better as we know, and compile to bytecode for execution on the EVM. Data structures. Ethereum state is stored locally on each node database, usually Google level DB. So this is important to understand that Ethereum has a database internally, and in this case, he's talking about Google level DB, but could be anything really, which contains the transactions in system state in a serialized hash data structure called Merkle-Patricia tree. Okay, Ethereum core component. So let's just go back to this one because it's important, just to. So P2P network, transactions, state machine, and data structures. So I guess the place to save the information, how the information gets changed, and what kind of actions actually start that state change and the network itself. Cool. Let's go to the Ethereum core components. Consensus algorithm. Ethereum uses Bitcoin consensus model, Nakamoto consensus, which uses sequential single signature blocks weighting by the importance by weighting by sorry, I'm gonna repeat that. Ethereum uses Bitcoin consensus model, Nakamoto consensus, which uses sequential single signature blocks weighted in importance by proof of work to determine the longest chain, therefore the current state. Okay? So I'm gonna read that again because I didn't really understood. Ethereum uses Bitcoin consensus model, Nakamoto consensus, which uses sequential single signature blocks. So I guess we're talking here on how each block hashes is hashed by the last block, weighted in importance by proof of work to determine the longest chain, therefore the current state. Awesome. So now I understood it. However, you guys are still there? Can you guys hear me?
Yes, we can hear you.
Yeah, loud and clear. Yeah.
Okay, awesome. Consensus. So let's go. However,
Yes, yes.
awesome. However, this is being transitioned to proof of stake algorithm in Ethereum 2.0. This has already happened, so we are in the future, okay? Economic security. Ethereum currently uses a proof of work algorithm called ETHash, but this is being transitioned to a.
You should
Go on.
uh, you should focus on EVM and like
No,
high
no, no,
level
Rush.
languages like Solidity.
No, no, no. So let me explain what
Okay.
we are doing. I'm gonna explain to you. What we are doing is we are covering the Secureum from start to finish. We're not focusing on the EVM part. We're gonna go through everything, But the idea is actually going over these points again because often we go advance, but there's a lot of content for that. So I just want to cover this, so we can cover everything. But definitely, I'm taking a look at what you're saying, and we're gonna have a lot of EVM stuff to come. Okay, so yeah, so it's gonna happen. Clients.
Okay, cool.
No, no problem. Ethereum has several interoperable implementations of the client software. The most prominent are Go Ethereum and Open Ethereum. The others are Aragon, Nethermind, Tubergit. Open Ethereum is being deprecated in transition to Aragon, which is former Tubergit. Can anybody explain me Aragon here? No, right? Let's go to Google. What is Ethereum Aragon? Aragon is a complete re-architected implementation of Ethereum, currently written on Go, but with implementations in other languages under development. Aragon's goal is to provide a faster, more modular, and more optimized implementation of Ethereum. Okay, so now we know what Aragon is. Ethereum ability to execute a storage program in a state machine called the Ethereum virtual machine while reading and writing data to memory makes it a Turing-complete system. A Turing-complete system faces the challenge of the halting problem. Given an arbitrary program and its input is not solvable to determine whether the program will eventually stop running. So Ethereum cannot predict if a smart contract will terminate or how long it will run. Therefore, to constrain the resources used by the smart contract, Ethereum introduces a metering system called gas. This is also super important. As the EVM as the EVM executes a smart contract, it carefully accounts for every instruction, computation, data access. Each instruction has a predetermined cost in units of gas. When a transaction triggers the execution of a smart contract, it must include the amount of gas that sets the upper limit of what can be consumed running that smart contract. The EVM will terminate the execution if the amount of gas consumed by the computation exceeds the amount of gas available in the transaction. Gas is the mechanism Ethereum uses to allow Turing-complete computation while limiting resources that any program can consume. Ether Ether needs to be sent along with a transaction and it needs to be explicitly marked for the purchase of gas. I wonder what it means. That means every transaction needs to have some gas, right? Along with the acceptable gas price. Just like a pump, the gas price is not fixed. The gas is purchased for the transaction, the computation is executed, and the unused gas is refunded back to the sender. A decentralized application, abbreviated as DApp or DApp, is a web application that is built on top of open, decentralized, peer-to-peer infrastructure services and typically combines smart contracts with a web interface. dApps represent a transition from Web 2.0, where applications are centrally owned and managed, to Web 3.0, where applications are built on top of decentralized peer-to-peer protocols for computing. So if anyone is watching this and don't really understand the difference between Web 2 and Web 3, basically Web 3 is everything running over a blockchain. Some people would say, we'll give you different and complicated explanations for that. It can even be maybe acceptable, but the idea here is simply that one second, let me close this. We're running over a blockchain, so especially Ethereum, because of the decentralization part. Okay, so the Ethereum blockchain represents the decentralized compute part of Web3. Swarm represents decentralized storage, and Whisper, now Waku, represents the decentralized messaging protocol. We don't even use these things anymore, right? Decentralization can be considered as three types: architectural decentralization, political decentralization, and logical decentralization. I guess we could be talking about multi-sigs, governance, and I don't know this one. Could be explaining a little bit about each one of these here would be nice to know. Let me see if I can. So let's see if, so architectural. How many physical computers is need as man. How many physical computers is a system made up of? How many of those computers can it tolerate breaking down at any single time? One second. There's a lot of people here. Hey Scroll, how's it going, brother? Let's see political decentralization. How many individuals or organizations ultimately control the computers that the system is made up of? And logical decentralization. Does the interface and data structures that the system presents and maintains looks more like a single monolithic object, or is amorphous swarm? What a fucking one simple heuristic is, if you cut the system in half, including both providers and users, will both halves continue to fully operate as independent units? Okay, I got it. So we're talking about a little bit of redundancy and resilience when we talk about logical decentralization. Let's keep on. Ethereum currency unit is called ETH. So this is also something important. Ethereum and ETH are different things. Okay, Ether is subdivided into smaller units, and the smallest unit is named Wei. Okay, so you have one Babbage, one Lovelace, Shannon, and all these names I think are changed now for the names of Nico, Szabo, Ethereum uses public key cryptography to create public key pairs considered a pair because the public key is derived from the private key, which are not used for the encryption but for the digital signatures. Okay, Ethereum uses the elliptic curve digital signature algorithm for digital signatures, which is based on the elliptic curve cryptography, an approach to public key cryptography based on the algebraic structure of elliptic curves over finite fields. Ethereum private key is a 256 random number, 256 bit random number that uniquely determines single Ethereum address, a single Ethereum address, also known as an account. An Ethereum public key is a point on the elliptic curve calculated from the private key using the elliptic curve multiplication. One cannot calculate the private key from the public key. Ethereum state is made of objects called accounts, each account having a 20-byte address and state transactions being direct transfers of value and information between accounts. So state transactions being direct transfers of value and information between accounts. Okay? Ethereum can contain 4 fields: the nonce, account are used to make sure each transaction only happens once, the current balance, the contract code, which is the code hash, right? And the account storage, empty by default. Ethereum has 2 types of accounts: externally owned accounts, controlled by private key, and contract accounts. So here we're talking about wallets and contracts, and every time you see the term EOA, someone is talking about a wallet with a fancy word, okay? The ownership of Ether by EOA is established through private keys, Ethereum addresses, and digital signatures. Anyone with a private key has control of the corresponding EOA account and any Ether it holds. An EOA has no code, and one can send messages from EOA by creating a sign-in transaction. A contract account has code associated and associated storage. Every time it receives a message, its code activates. Its code activates, allowing it to read and write to internal storage and send messages to create a contracts in turn. Smart contracts can be thought of as a non-autonomous agent that lives inside of the Ethereum execution environment, executing specific pieces of code when poked by a message or transaction and having direct control of their Ether balance or their own key value stored to keep and persist variables. Ethereum uses kcheck 256 as its cryptographic hash function. Kcheck 256 was a winning candidate for the SHA-3 competition held by NIST, but it's different from the finally adopted SHA-3 standard. Ethereum address of an EOA account is the last 20 bytes, the least significant bytes of the kcheck 256 of the public key of the EOA key in pair. Transactions are signed messages originated by an EOA, transmitted by the Ethereum network, and recorded on the Ethereum blockchain. Only transactions can trigger a change of state. Transaction properties. They are atomic. It's all or nothing, cannot be divided, interrupted by other transactions. Serial. They are processed sequentially, one after the other, without any overlapping. Inclusion. Transaction inclusion is not guaranteed, depends on the network congestion and gas price, among other things. Miners determine inclusion. Order. Transaction order is not guaranteed, depends on the network congestion and gas price, among other things. Miners also say the order. A transaction is serializable. A transaction is a serializable binary message that contains the following components: a nonce, so the sequential number; the gas price, the amount of Ether that the originator is willing to pay for each unit of gas, okay? Gas limit, the maximum amount of gas that the originator is willing to pay for this transaction. Okay, so here's for the unit and here's for the transaction. Recipient, who's receiving that transaction, let's say, yeah, because every transaction is going to somewhere, right? Value, the amount of ether in way to send to the destination. Data, the variable length binary data payload. VRS, the three components of a ECDSA digital signature of the originating EOA. Nonce, a scalar value equal to the number of transactions sent from the EOA account. In case of contract account, it is the number of contract creations made by the account. This is really interesting point. You guys need to pay a lot of attention on this one. So the nonce inside the smart contract is the amount of contracts that contract created. It's not the number of transactions, not the number of the transactions, but the amount of contracts created inside that contract. Okay, gas price. Now we know what is gas price. We know what is gas limit. We know about the recipient. Let's jump to the next thing. Here. A digital signature serves three purposes in Ethereum. Proves that the owner of the private key, who is by implication the owner of an Ethereum account, has authorized the spend of Ether or execution of a contract. Guarantees no repudiation, meaning the proof of authorization is undeniable. Proves that the transaction data has not been and cannot be modified after the transaction has been signed. Contract creation. Contract creation transactions are sent to a special destination address called zero address. A contract creation contains a data payload which is the compiled bytecode to create the contract. An optional ether amount in the value field will create the new contract with a starting balance. So you can send some ether with the contract creation, as long as you make the constructor payable or have a payable fallback function. I don't know if that works too. Transactions versus messages. This is a very interesting one. Okay, so a transaction is produced by a UA, meaning a wallet, where an external actor sends a signed data package which 1. Triggers a message to another UA where it leads to a transfer of value, or 2. Triggers a message to a contract account where it leads to the recipient of the contract running its code. So a transaction is the signing of the message and the sending, but it's not the message itself. The message is triggered by a transaction to another UA or account, triggered internally within the EVM by a contract account when it executes a call, family of opcodes, and leads to a recipient contract running its code or value transfer to the recipient EOA. So the message is the context inside it. So the transaction sends the message, and whenever you are inside the solidity function, you're always gonna have that message dot, different kinds of information in there. So that's the message itself, okay? Transactions are grouped together into blocks. A blockchain contains a series of such blocks that are chained together. Blocks are batches of transactions with a hash of the previous block in the chain. They link blocks together in a chain because hashes are cryptographically derived from block data. This prevents frauds because one change in a block in history would invalidate all the following blocks, and all subsequent hashes would change, and everyone running the blockchain would notice. I'm gonna read that again, okay? Blocks are batches of transactions with a hash of the previous blocks in the chain. So this is already something really important. They gotta be, binded on your mind, okay? These links blocks together because hashes are cryptographically derived from block data. Okay, so we are using the data of the block to create the as a seed for the encryption. Okay, this prevents fraud. Okay, maybe seed for the encryption wasn't the best description. This prevents fraud because one change in any block in history would invalidate all the following block, as all the subsequent hashes would change and everyone running the blockchain would notice. To preserve the transaction history, blocks are strictly ordered. Every new block created contains a reference to its parent block, and transactions within blocks are strictly ordered as well. Ethereum Node Client is a node software application that implements the Ethereum specification. There's another piece of information here. Ethereum is not a software. Ethereum is a specification. You can go over the specification and build your own software. So it's wrong to say that Ethereum is a program or it's a software. Okay, communicates over a peer-to-peer network with other Ethereum nodes. A client is a specific implementation of the Ethereum node. Two most common client implementations are Give and Open Ethereum that we know it's being deprecated. Ethereum transactions are sent to ETH nodes to be broadcasted across a peer-to-peer network. Awesome. Miners. Miners are entities running Ethereum. Yeah, entities. Okay, we can think on anyone. I mean, I know entities mean anyone, but just if there's a newcomer there, anybody can be a miner as long as you have the money and the patience. Miners are entity running the Ethereum nodes that validate and execute these transactions and combine them into blocks. The process of validating each block by having a miner provide a mathematical proof is known as proof of work. Miners are rewarded for blocks accepted into the blockchain with a block reward. Currently, to Ethereum, a miner gets fees, which is the ether sent to spend gas on by all the transactions included in that block. So besides getting the price, the constant you get is the fees, for processing each one of the blocks. Okay. Block as limit is set by miners and refers to the cap on total amount of gas expended by all transactions in the block, which ensures that the block cannot be arbitrarily large. Blocks therefore are not fixed in size in terms of number of transactions, because different transactions consume different amount of gas. Blocks take time to propagate through the network, and multiple miners are simultaneously producing valid blocks. This leads to the blockchain considering multiple blocks at the same level, but ultimately choosing only one block at any level that creates a canonical blockchain. This choice is dictated by Ethereum greedy heaviest observable. I'm gonna read that again, okay? Blocks take time to propagate through the network, and multiple miners are simultaneously producing valid blocks. Awesome. This leads to the blockchain considering multiple blocks at the same level, but ultimately, ultimately choosing only one block at any level that creates a canonical blockchain. This is a really interesting point too, if you think that multiple blocks are at the same level, but we need to choose one of those. This choice is dictated by Ethereum greedy heaviest observable subtree Ghost protocol, which includes tail blocks up to 7 levels in the calculation of the longest chain. Stale blocks are called uncles or ummers. So I think everybody heard before about uncle blocks. Consensus. Decentralized consensus in the context of Ethereum refers to the process of determining which miners. Oh, I have a Viper lesson after this. Okay, just remind me. Uh, Decentralized consensus in the context of Ethereum refers to the process of determining which miner's block should be appended next to the blockchain. These involve two key components, proof of work and the longest chain rule. Miners apply these rules to build on the canonical blockchain, and this is referred as the Nakamoto consensus, which is adapted from Bitcoin. State is a mapping between addresses and account states implemented as a modified Merkle tree or tree. A Merkle tree or tree is a type of arbitrary binary tree composed of a set of nodes with leaf node. Leaf nodes are at the bottom of the tree that contains the underlying data. Intermediate nodes, where each node is the hash of these two child nodes, and a single root node is formed from the hash each is of its two child, representing the top of the tree. Ethereum proof of work algorithm. Let me see what's Ethereum's proof of work algorithm called ETHhash, previously known as Dagger Hashimoto. Yeah, we actually changed that. We don't even use that anymore, but I'm gonna cover here anyway. The algorithm is formally defined as this, where HN is the new block header, but without the nonce and the mixed hash components. HN is the nonce of the header. D is the large data set needed to compute the mean hash, and HT is the new block difficulty value. POL, proof of work function, which evaluates to an array, which is the proof of work function, which evaluates to an array with the first item being the mixed hash and the second item being the pseudo-random number, cryptographically depending on H and D. Okay, I understand nothing about this. Blocks contain block header, transactions, Ulmer block headers, and block header contain part hash, so the hash of the block before you, Ulmer's hash, the hash of the list of the Ulmers or uncles, right? The beneficiary, a 160-bit address to which all fees collected from the successful mining of the block will be transferred. State root. So just so remember, we're talking about a block, okay? State root. The check 256 hash of the root of the node of the state trie after all transactions are executed and finalizations are applied. Transaction root. The check 256-bit hash of the root node of the trie structure populated with which transaction in the transaction list portion of the block. Recipient's root was again a check 256 hash of the root node of the trie structure populated with the recipient of each transaction. Okay, and the Bloom filter, this one is very interesting. Ethereum logs, they use a Bloom filter, which is a type of filter that never tells you if the information is really there. It's just really good at telling that the information is not really there and it may be there. And that allows for much faster indexing whenever running these things. And now a small trick here. Sometimes it's faster to store things in events than in the contract state. So think about that. Okay. The Bloom filter is composed from indexable information contained in each log entry from the recipient of each transaction in the transaction list. Difficulty. A scalar value corresponding to the difficulty level of this block that can be calculated to the previous block difficulty level. And just to talk a little bit about this difficulty concept, imagine that I need to find, so I'm a blockchain, right? And I need to find the next block. I'm gonna open really fast here my multimedia thing. Where is it? Office, right there. Okay, let me open this. Let me try to show you guys what I'm talking about. Okay. So imagine this. I'm a blockchain and I'm talking about difficulty, okay? So the quest here is to validate the next block. But I can only validate the next block using, let's say, proof of work if the next block starts at 1-0. So whatever block I get, if it starts with 1-0, is my block. I can validate it. Now, if I increase the difficulty, I could say now I want one to start with 3 zeros. Then it's much harder to find this block. Then I can say, hey, give me one with 5 zeros. So pretty much that's a way to increase the amount of computation power needed to find the next block. Okay, let's go back. Number. A scalar value equal to the number of ancestor blocks. The genesis block has number of 0. Gas limit. A scalar value equal to the current limit of gas expenditure per block. Gas used. A scalar value equal to the total amount of gas used in this block. 1 second. Awesome. So extra data, an arbitrary byte array containing data relevant to this block. This one I never knew. Timestamp. The timestamp, the Unix time of the block inception. This one, before proof of stake, we had much less consistent block time on Ethereum, and now we have like a really consistent block time. Don't know exactly what that means in terms of DeFi experience, but I guess it's good, right? So extra data is an array containing data relevant to this block. Interesting. I wonder, maybe some parameter or something of the function. The mixed hash combined with nonce proves that a sufficient amount of computation has been carried out for this block. Interesting too. Nonce, a 60-bit value which combined with mixed hash proves that a sufficient amount of computation has been carried out in this block. Wait a second. I think they got it wrong here, right? Because they have the same text from this and this. Or maybe it's some close information, I don't know. State root, transaction root, and no, wait a second again. Look, combine it with the nonce. So those are combined to prove that, so I have the nonce, meaning that this is the number of the transaction, and the hash, which is the proof of all the computation that happened in there, okay. State root, transaction root, recipient root are 256-bit hashes of the root nodes of the modifier Merkle-Patricia trees. The leaves of the state root are key-valued pairs of all Ethereum address account pairs, where each respective account consists of nonce, a scalar value equal to the number of transactions from this address in the case of account associated with code, the number of transaction creations made by this account. Balance, a scalar value to the number of way owned by this address. Storage root, a 256-bit hash of the root node of the modifier Patricia tree. Whoa, bro, I don't even know what we're talking about. Let me go back. Ethereum address account pairs. This is important, okay? No, we're talking about state root, transaction root, and receipt. So we're talking about the proofs of the transactions in state, of the changes in state, the transactions and the recipient roots, okay. And they are saying that state roots are key pairs of all Ethereum address account pairs, which each respective account consists of. So now we're talking about details of the account itself. Nonce, how many transactions, okay? Balance, how much ETH in that account. Storage root, let's read this one. That encodes the storage contents of the account, encoded into a trie mapping for our, I wonder, the code hash of the EVM account. Okay, I think storage root is just for contract, just for EOAs, and code hash is always 02 for EOAs. No, this is just for not EOA, non-EOA, so contract accounts, and these two. So this will be 0, and this will have nothing, because the code hash is the hash of the smart contract code, more like an ID that is used to fetch the code of the smart contract in the Ethereum database. Okay. Transaction receipt is a tuple of 4 items comprising the cumulative gas used in the block containing the transaction receipt of as of immediately after the transaction has happened, the set of logs created through, we're talking about transactions receipt, okay? So we're talking that transaction receipt is a tuple of 4 items having the cumulative gas using in the block containing the transaction receipt as of immediately after the transaction has happened, the set of logs created through the execution of the transaction, the Bloom filter composed from the information in those logs, and the status code of the transaction, so if that reverted or not. Gas refund and beneficiary. So we know that any unused gas in the transaction is going back to the beneficiary. Okay, let's see what's written here. Any unused gas in the transaction is refunded to the sender of the account at the same gas price. Ether used to purchase gas for this transaction is credited to the beneficiary address specified in the block header. So this is a very like interviewee, like senior interviewed question, like, you know, because it's a really tricky small thing that you really need to, you know, like, so if I come to you and I ask you, okay, where are the information of the beneficiaries, and you know you gotta need to tell me that that is in the block header, you know, so just something that you guys gotta. So the address of an account, typically under the control of the miner, this is the transaction fees paid to the miner. Let me just read that again. Ether is used to purchase gas for the transaction is credited for the beneficiary address. The address of an account, typically under the control of the miner. This is the transaction fees paid to the miner. Okay. Okay, so we're talking about different things here. Gas refund is something that happens in the smart contracts. So you get the gas as, you know, you don't spend it all. And beneficiary is the miner that mined the block, so he's getting all the fees, you know, in the transaction. Okay. So let's go for the EVM part. EVM is a quasi-Turing complete machine where the quasi-quantification comes from the fact that the computation is intrinsically bounded through a parameter gas, which limits the total amount of computation done. EVM is the runtime environment of smart contracts. The code in Ethereum contracts is written in a low-level, stack-based bytecode language, referred as the Ethereum Virtual Machine Code, or EVM code. The code consists of a series of bytes, hence called bytecode, where each byte represents an operation. The EVM is a simple stack-based architecture. Another interview question here, okay? The EVM is a simple stacked architecture consisting. The EVM is a simple stack-based architecture consisting of the stack, volatile memory, non-volatile storage with a word size of 260 bits, and call data. Rush. The EVM is a simple stack-based architecture consisting of stack, volatile memory, non-volatile storage with a word size of 260 bits, and the call data. And this was chosen to facilitate the check hash scheme. Stack is made up 1024 256 bits elements. EVM instructions can operate with the top 16 stack element. Most EVM instructions operate with a stack-based architecture, and there are also stack-specific operations like push, pop, swap, and I think here we're gonna push something into memory, pop, you're gonna remove something from a last, remove the last of the first line, I don't know. Dup swap will exchange some bytecode and dup will duplicate it. Seems complicated, but once you learn these things, they are not that hard. Memory is a linear byte array addressable at a byte level and it's volatile. All locations are well defined initially as 0. This is accessed with mload, mstar, mstar8 instructions. Storage is a 260-bit to 260-bit key value store. Unlike memory, which is volatile, storage is not volatile and is maintained as part of the system state. All locations are well defined initially as 0. This is accessed with sload and storage. So storage load and storage store. Call data is a really only byte addressable space where the data of the parameter of a transaction or call is held. Let me go back to that again. Call data is a read-only byte addressable space where the data parameter of a transaction or call is held. This is accessed with call data size, call data load, and call data copy instructions. Raj, you there? Okay, no problem. The EVM does not follow the standard for von Neumann.
Hello. Yes, I am here, brother.
Can you can
I have joined with mobile.
can you explain for us a little bit about this call data thing here?
Yeah. So whenever someone sends transaction, the call data is, the payload which user do,
Okay,
like
the payload.
transfer. So
Nice.
it contains the 4-bit signature and, like parameters for the functions, right?
Okay, very
And
nice.
yeah, signatures tells EVM like which function to call, right? So yeah,
Thank you, bro.
and we have some opcodes, call data size. It tells the size of call data, which can be of any size, minimum of 4-bit, I think, like, right?
Yeah,
Yeah, for the function.
yeah, the
Yeah,
signature.
and call data load the call data from call data location, and call data copy also, like do the call data like copies the call data, right?
Really nice. Let's go. Thank you, Raj. The
Most
EVM does
welcome.
not follow the standard of von Neumann architecture. Rather than storing the program code in a generable accessible memory or storage, it is stored separately in a virtual ROM accessible only through specialized instruction. EVM uses bin endian ordering, whether the most significant byte of a word is stored at the smallest memory address and the least significant byte at the largest. The EVM instruction set can be classified into 11 categories: stop and arithmetic operations, comparison and bitwise logic operation, SHA-3 environmental information, block information, stack, memory, storage, and flow operations, push operations, duplication operations, exchange operations, log operations, and system operations. This is really useful. Huh? This is really nice. A really nice rundown of everything you have in the EVM. Um, Stop and arithmetic operations, opcode, mnemonic, stack items remove, or stacking items place, description. So, 00 halt execution, 0x01 adds to 1, adding operation, 002 multiplication operation, 03 subtraction operation, 04 division, 05 signer, 06 modulo, 07 signed modulo, 08 modulo addition and modulo multiplication at 09, and 0x0a is an exponentiation, and 0x0b is a sign extend. The comparations are, this is so fucking cool. Um, 0x10 for a less than comparison, 0x11. I'm gonna even copy this and paste this on the. This is fucking gold. I'm gonna paste this on the Learn EVM channel. Hey
Is
Ronin,
it the
nice to see
same
you,
as
bro.
at
Here, fast, fast EVM view. Oh, really? No problem. Let's go back. So 0x12 less than, 0x13 greater than, 0x14 equality, 0x15 is 0, 0x16 bitwise, 0 bitwise AND, okay, 0x70 bitwise OR, 0x18 bitwise XOR, 0x19 bitwise NOT, 0x1A retrieves a single byte from word, 0x1B left shift operation, and 0x1C logical right shift operation, 0x1D arithmetic sign right shift operation, SHA-3 mnemonics text eating remove eating split. Let's take a look. 0x, so SHA-3 is 0x20, okay, and let's go for the environmental information, okay. So 0x30 gets address of current execution account, 0x31 gets the balance of given account, 0x32 gets the execution origination address, so this is like the tx.origin. 0x33 gets the caller address. The caller could be a contract, could be a leeway. 0x34 call value gets deposited value by the instruction. So this is message.value that we're talking here. 0x35 call data load get input data of the current environment. 0x36 call data size get the size of the input data of the current environment. So loading the payload, seeing the payload size, and copying the payload into memory. Okay, so 0x35, 36, and 37. 0x38, the code size, gets the code size of the current implementation. You can also see these at whenever you convert something to an address, you always have the code.code thing in there that you can load to see the code of the contract. Code copy, copy code running in an environment to memory. Gas price, what is the gas price of the execution? Is it code data size? Get the size of the account's code. Actually, also I was mistaken maybe because I was thinking of that. This is actually this. Is it code copy? Copies an account code to memory. Return data size. Gets, this is all 03B, 0x3C, and now we're doing 0x3D, which gets the size of the output data from the previous call from the current environment. Which 0x3E, return data copy, copy the output data from the previous call to memory. 0x3F, is it code hash, gets the hash account, gets hash of an account's code. Now let's go for the block information, okay? 0x40 block hash gets the hash of one of the most, get the hash of one of the 256 most recent complete blocks. Gets the hash of one of the 256 most complete blocks. I don't think I understood this one. Coinbase gets the beneficiary address. So whenever you see the block Coinbase is the miner that actually effectively mined that block. timestamp gets the block timestamp, number gets the block number, difficulty gets the block difficulty, gas limit gets the block gas limit. So this is all 041, 042, 043, 044. So now when you guys see bytecode won't be so maybe so scared anymore. Stack, memory, storage, and flow operations. I wonder what they mean with flow operations. Maybe setting a variable, or deleting something. So 0x50 pop removes an item from the stack. 0x51 mload, mload loads a word from memory. Mstar saves words to memory. 052. 053 mstar 8 save bytes to memory. Sload 0x54 loads from storage. 0x55 saves word to storage. 0x56 jump alter the program counter. 0x57 conditionally alter the program counter. 0x58 get the value of program counter prior to the increment of corresponding this instruction. 0xpc gets the current value of the program counter. Interesting, this one is interesting. 0x59 m size gets the size of active memory in bytes. 0x5a gets the amount of available gas, including the corresponding reduction for the cost of the instruction. 0x5b jump test mark a valid destination. Hey, how's it going?
Yeah, I just had a doubt.
Go
What
on.
is the after yeah, could you just open the that what is that? There's like two digit number, right? That comes after, for example, after push there is like 0 1. What does that mean?
I
Yeah,
don't really know, but I maybe could be that 1 1 right here. You know what is this, Raj? I don't really
yeah,
know. I think this was copied from somewhere, maybe, and then he had these. I don't know. Doesn't seem to me like this is a. Doesn't seem to me like this is something that is used again together with the bytecode. Okay. So maybe we don't even need to
yeah,
worry
okay.
up with that. Okay. But it's alright. You're making the right question. Is that I mean.
Yeah, it's okay. So I think you guys are reading all the opcodes, and if you wanna get like more detail, you guys can check evm.codes, and we have one more code which is like push zero, which which is of 2 byte, and yeah, which adds a zero onto the stack with two gas only. So yeah, yeah,
Maybe that's the gas. Maybe that's the gas cost. No.
Oh, okay, okay. Yeah, thanks.
Maybe no. I don't know if that's the case. Okay. I know that
okay.
here.
Like, can you show me like what was the doubt?
Here, look. We have after each bytecode we have these numbers. Like we have 0 1, 1 1 0 here, 2 0, and we don't know what this means. If this is the gas cost or something.
Okay, yeah, even I don't know like what does
Yeah, I
it mean,
think this
right?
is not key. So let's just keep going, and then we can, when we start doing the exercise, we see if this is wrong or not. So let's go for the last one was m size gets the size of active memory in bytes. Someone's no, will not cannot talk right now. Gas gets the available gas, including the corresponding reduction for the cost of this instruction. Jump dash mark a valid destination for jump. This operation has no effect on the machine state during the execution. Push description, push operations. 0x60, push 1, places 1 byte into the stack. 0x61, push 2, places 2 bytes into the stack. Push 3, push 4, push 5, and push 31. They pull until 31 bytes into the stack. 0x7f, push 32, places a full world, 32 bytes, 32 byte into the stack. Duplication operations, those are the fun ones, 0x80, dup1, duplicates the first item of the stack. And you have that until 0x8f, which duplicates the 16. Remember that we work only with the 16 first stack positions. No, not first, but we only work with 16 stack positions at a time. Exchange operations, swap 1. So you can swap, because you're doing only 16, you can swap like some memory places, just for some time, so you can do an operation more efficiently. So, and you have swap 2, which swaps the first and third stack items. And then you have, swap 3, swap 4, swap 15, and choose 0x9f, which is, swap the first with the last item. Login operations. This one is really interesting. And here we can also think about the maximum amount of indexed words you can have in Solidity. I don't know if this is 3 or 4. I think it's 3, the maximum for an event. Or I think it's 4. Maximum indexed parameters, Solidity. Why I'm using these? Why I'm not on ChatGPT, man? Why I'm using this fucking old shit? Okay, uma coisa interessante. There's something interesting here. Before Solidity 8, you could use up to 4 indexed parameters. And now, after Solidity 8, you can only use 3. So here you're going to have the operations for 0x08, no topics. 0x02 with 1 topic, 2 topic, 3 topics. And I think those topics relate to the way the events are indexed. So very interesting. System operations. Creates a new account with associated code. 0xF0. 0xF1. Call. Message call into an account. Call code. Message call into this account with an alternative account code. 0xF3. Halts execution, return output data. Here's the dangerous one. 0xF4. Delegate call. Message call with this account with an alternative account code but persisting the current value. So remember, delegate calls keep context, so the message will be intact with its value, with its sender. So careful when importing code into a smart contract, because that's what you do when you're doing a delegate call. 0x5f, create 2, creates a new account with associated code. 0xfa, static call, static message call into an account. It would be really nice to get the difference here, but when we're talking about static calls, we're usually talking about pure and view functions. So keep that in mind. Revert, classic one, a lot of headache for everybody. The revert operations, they are also here. 0xfe, invalid. 0xff, self-destruct. This one is deprecated. And I really think that this is the gas cost of the operation, because you have here, I know the create is three way to to execute, and here we have the, so here we actually seeing the gas cost. Was just not so maybe explained. So let's go for the,
Can you scroll up?
yeah,
Scroll up little bit.
look, create tree
Like
calls.
first is opcode, then we have mnemonic, then we have stack items removed, then we have like stack items placed.
No, no, no. Opcode. Ah, yeah. Thank you, Raj. Opcode, mnemonic, stack, stack items removed. Yeah, because you're using three
Yeah,
items.
like create takes three items
Yeah,
from the top of the stack and place one item on the top of stack, right? So yeah.
yeah, yeah. Nice. Thank you, bro. That was actually what we needed. Description. Nice. Okay, let's keep on. So now we're gonna talk about gas cost instructions. Okay, and let's. Okay, so stop, invalid, and revert are at zero gas. So that we know. Most arithmetic logic are between 3 and 5 gas. Call, balance, and exit are 2600 gas. Mload, mstar, and mstar 8 are 3 gas. Okay. Sload is 2100 gas, and SS star is 20,000 gas to set storage from to set storage slot from 0 to non-zero. And oh, sorry, I'm gonna read that again. S load is 2100 gas, and SS star is 20,000 gas to set a storage slot from 0 to non-zero, and 5,000 gas otherwise. Okay, so it's important to know that the first time you're doing a store, an SS store, there's no cache. So what's our better yet? The information is not properly indexed in the code hash, or maybe not in the code hash, but in the storage hash. And with that, it's harder to make the operation. So after you set it the first time, it's gonna cost only 5,000 for subsequent operations. Okay, so it's important to know that. Create is 32,000 gas, and self-destruct is 5,000 gas. Okay, a transaction reverts for different exceptional conditions, such as running out of gas, invalid operations and constructions, in which case all state changes are made are so far, in which case all state changes made so far are discarded and the original state of the account is restored as it was before this transaction executed. A transaction with a contract address destination has the contract function target and its required arguments in the data field of the transaction. These are encoding according to the application binary interface. Application binary interface. The contract application binary interface is the standard way to interact with contracts in the Ethereum ecosystem, both from outside the blockchain and for a contract to contract interaction, so starting from a wallet or operations between contracts. Okay, interface functions of a contract are strongly typed null at compilation time and static. Okay, so what this means is that he's going to be copying that code during the compilation, I guess. Contracts will have the interface definitions of any contracts they call available at compile time. The function selector. The first 4 bytes of the call data for a function call specifies the function to be called. It is the first 4 bytes of the keycheck hash of the signature of the function. The signature is defined as a canonical expression of the basic prototype without a data location specifier. The function name with the parentheses with the parenthesized list of parameters types. So I'm going to read that again. The signature is defined as the canonical expression of the basic prototype without the data location specifier. The function name with the parenthesized list of parameters type. Parameters types are split by a single comma. No spaces are used. Look at this. No spaces are used. Function arguments. The encoded arguments follow the function selector from 50 byte onwards. Block Explorer are portals that allow anyone to see real-time data. We know what a Block Explorer is, right? Mainnet, we know what mainnet is. We know what the IPs are. Anybody has any questions on this? Kashif? Annie? Anybody has any questions? Hey Igor, how's it going? No question? Okay, we know what is a block explorer. I'm gonna go through that really fast because, yeah, Etherscan, so you can see what happened in the block, you can check the transactions and everything. Mainnet is the main network of the Ethereum protocol, and you also have different test nets where you can run and test your software. So you have Curly, which is proof of authority. Proof of authority is a consensus system that you define who's going to be validating the blocks. And there's also some governance involved in who's going to be added as a validator. Coven, also proof of authority. Rigby, I think, isn't Rigby that? I think Rigby could be that, okay? I think now we only have Gorley and Seporia and Robstein, I think. Yeah, you need to check. But these are all test nets. Then we have EIPs, Ethereum Improvement Proposals, which are... what is the best way of explaining that? Exactly, it's an improvement proposal going over some aspect of the specification and adding, you know, or removing certain details or parts to the specification. So let's give it a read here. The Ethereum Improvement Proposal describes standards for the Ethereum platform, including core protocol specifications, client APIs, and the contract standards. Standard track EIPs are separated into number types. Core improvements requiring a consensus fork, as well as changes that are not necessarily consensus critical but may be relevant to core dev discussions. Networking includes improvements around dev P2P, light Ethereum subprotocol, as well as proposed improvements to the network protocol specification of Whisper and Swarm. Interface includes improvements around client, API RPC specification standards, and also certain language level standards like method names, contract APIs, and the label interface aligns with the interface repo, and the discussion should primarily occur in that repository before an EIP is before it's remitted to the EIP repository. Awesome. ERC, application level standards and conventions, including contract standards such as the token ERC20, ENS name system, and so on. Okay, URI schemes for NFTs. Meta describes the process around Ethereum or proposes of change to a process. Information describes a Ethereum design issue or provides a general guidelines or information to the Ethereum community, but does not propose a new feature. So just to make it clear, we're talking about the types of EIPs that you're gonna find. Okay, so we're talking about Ethereum 2 here, which is probably the merge. Let's go for the immutable code. Immutable code, once a contract code is deployed, it becomes immutable. Standard software development practices that rely on being able to fix bugs and add new features to the deployed code do not apply here. This represents a significant security challenge for smart contract development. There are three exceptions. The modified contract can be deployed to a new address. Okay, we know this one. The modified contract can be deployed as an implementation of proxy pattern. So if you're using a proxy, you can just change, you know, the address of the implementation. And if there's anyone that doesn't know what a proxy is here, it's basically a contract that processes part of the code or stores part of the storage in another contract. So allows you to make some level of upgradability, sometimes too much. Create to allows updating in place using create to opcodes allows updating in place using the init code. I don't get this one. I wonder if this is create a new contract, you know, something like that. Web3, you know what Web3 is, you know, Dogecoin, Shiba Coin. Languages, Web2, not important. On-chain versus off-chain. So this is important. A lot of things happen off chain. Most of our applications still Web2 based, so they're still running some React and some AWS server and just talking to a smart contract. So a huge part of Web2 is still Web3 is still Web2. Regarding off-chain stuff, you're gonna see these through all kinds of applications. You're gonna see this being used in bridges. You're gonna see this being used for things like protection, defense. You know, like someone just took too money out of a protocol. It's always nice to have. You can have some sort of automation looked at off-chain things, and yeah. So beware of that. Okay, open source and transparent. I guess one of the let's take a look at this one because they're probably talking something nice here. Open source and transparent. Given the emphasis on trust minimization, especially smart contracts are expected to be open source by default. The deployed bytecode is also expected to be source verified. Okay, so we need to, so everything is open and it's good that it's verified, you know. It's not required, but it's good. All interactions with smart contracts are recorded on the blockchain as transactions. These include the transaction senders, data, and outcome. Having complete visibility into the entire history of transactions and state transactions is akin to have a public accessible audit log. It's true, it's true. Furthermore, transactions that are still in flight and yet to be confirmed on the blockchain are also publicly visible. We're talking about the mempool in the pending transaction queues and leading to front-running attacks. Unstoppable and immutable. Decentralized applications are expected to be unstoppable and immutable because they run on a decentralized blockchain network, right? It's fucking ridiculous. This never happens. There should not be any entity that can unilaterally decide to stop running the app or make changes to it. Transactions and data on the blockchain are guaranteed to be immutable unless a majority of the network decides otherwise. Smart contracts in general are expected by the users to not have some kill switch controlled by the deployer, so nothing ideally shouldn't be able to stop the contract from paying or doing something. They're also expected to be arbitrarily upgradable. Both what? Okay, not arbitrarily upgradable. They are also expected to not be arbitrarily upgradable. Both these themes from the Web3 goal is trust minimization, lack of need to trust potentially malicious app developers. However, this makes fixing security vulnerabilities in the deployed code and responding to the exploit very challenging. Pseudonym teams and what we love the most here at OpenSense, DAOs. Perhaps inspired by Bitcoin Satoshi Nakamoto, there is a trend among some projects Web3 which is to be anonymous and use the picture of an anime girl. Okay. Okay, I'm gonna jump out this shit and let's go to new architecture, language, and toolchains. Ethereum has a new virtual machine, which is stack based. Okay, we know about this part. Solidity language, you know, much real competition. Viper is just so much better. The association toolchains include development environments like Truthful, Brownie, Hardhat, and more recently Foundry. Libraries, you know, like OpenZeppelin, the Solidity, the OpenSea libraries, and the GNU Safe libraries. Security tools like Slither, Mitro, MistyX, you know, Manticore, um, and wallets like MetaMask, you know, Elixir, and other wallets. Byzantine threat model. Now this is a good one. The Web3 threat model is based on Byzantine faults dealing with arbitrary, malicious behavior and governed by mechanism design. Given the aspirational absence of trust intermediaries, fuck, given the aspirational absence of trusted intermediaries, everyone and everything is meant to be entrusted by default. Participants in this model include developers, miners, validators, infrastructure providers, and users, all of whom could potentially be adversaries. This is a fundamentally different threat model from what Web 2, where there are generalized notions of trusted insiders with no authorized access to resources that they have to be protected against. With authorized access to resources, they have to be protected against outsiders. Web 3 is the zero trust scenario. Keys and tokens. So let me just yeah, we're talking about here, private key, keep your private key safe, and tokens. Now, what is a token? Let's go to the next one. Composability by design, permissionless innovation, censorship resistance, and core aspirational Web3. There are a number of compositized. Yeah, all these things we already know from compressed time scale. It feels like innovation in the Web3 space moves at a warp speed. Aspects of the transparent development and compatibility by design are a strong catalyst to accelerating permissionless, borderless participation. It is in further incentivized by internet native crypto economics tokens. Okay. This shrinks the innovation timescale in orders of magnitude. Well, there's a very beautiful way of putting it, where new waves of experiments happens over weeks, months, instead of years. It's very true. The compressed timescale has a tangible impact on security considerations during the design, development, and deployment. Corners are cut, shortcuts are taken, and the end result is poorly tested, holds millions of dollars worth of token, but is vulnerable to exploit. This is where we shine, right? Testing prod, a combination of compressed timescale, unrestricted composability by the Byzantine Treff model, and challenges of replicating a full state predicting failure replicating full state for predicting failure modes of interacting with components built with rapidly evolved experimental software, in many ways force realistic tests to happen only in production. This implies that complex and crypto-economic exploit may be discovered upon deployment. Audit as a silver bullet. Security software development lifecycle have evolved over several decades to a point where they're now expected to meet some minimum requirements of a combination of internal validation, external assets, and certifications depending on the value of the managed assets, anticipated risk, threat model, and market domain of the products. Web3. Web3 seems to increasingly rely on external audits as a stamp of security approval. This is typically justified by the lack of sufficient in-house security expertise, while optics of this approach falsely convince speculators. This approach, why? Oh my god, man. I can really understand what you're written here. Audits currently are very expensive, but the demand is much greater than the supply. Top-rated auditing team that have experience and reputation to analyze complex processes. This is completely true. Audits are typically commissioned once at the end of the project development, just before production release. So you're gonna get paid only after you did the whole audit. Upgrades to project go unaudited for commercial or logistical reasons. So if you audited your code and add some code to it, you're gonna have to audit that again, okay? That's exactly what happened, by the way, with someone, Euler, the other day. The expectation is that audits are a panacea for all vulnerability and the project is bug free. Okay, guys.